All right, now that we have categorized waves and we've described waves, what we want to do is talk about what waves do. And so my way of saying that is the properties of waves. And we'll see when we encounter those. And our very first property of a wave that we're going to talk about is something, a word that I'm pretty sure you know, and that is called reflection. So let's go back to my um, simulator here and talk about reflection. So we let this thing go. Notice there is nothing here that is a reflection. Actually, I'm going to turn this to a pulse so we can see things are going on. I can make a little pulse here. We're going to go normal. There you go. No reflections. But when I clamp off the end of this, we're going to see a reflection. So here we go. The pulse travels. Boom. There we go. And that is reflection. But what did we see? And exactly what did we see? Because I think a lot of people mistake reflection for something else. Notice here that when I make the pulse, this pulse is traveling to the right down the medium. Okay. Right. So it's traveling in this direction down the medium. And then when it hits this point where it's clamped off, we're going to call this point a boundary, right? So that's where one medium ends and another medium begins. So a boundary is going to be the interface between two media. You might not think of a clamp as a new medium, but when this wave energy gets here, it's going to try and wiggle the clamp. And so the clamp is potentially a new medium for a wave. It gets a little bit easier in some other examples to see a different medium or the interface between two media, but I'll show you those videos in just a minute. Okay, so the energy is propagating here to the right, and notice here, now the energy is propagating to the left. That's reflection. It is the change in the direction of the energy transfer when a wave encounters a boundary and the wave returns back into the original medium. It is very wordy, but that's what it is. Some people want to say it is the when a wave bounces off a boundary, but I don't like that phrase to bounce off. It's very convenient, but then you start thinking of the wave as hitting things, and then that sort of suggests that waves are things and that they're colliding, which is not true. The wave is just this pattern of energy transfer, right? So the fact that the wave energy was going in one direction and now it's going in another, that's the reflection. But hopefully you saw something else happen during that reflection, right? Did you see that the wave had an orientation that was, or the pulse had an orientation that was above the equilibrium line and then it was below an equilibrium line? There you go. That is not reflection. Okay. That is something that's called an inversion. And that only happens in this type of reflection. And what type is that? You'll notice here that the end here is fixed. Let me just get rid of this. If that end was loose, now notice here, there's still a boundary. This medium ends and something else begins. There's a ring on the pole here. And if I do this, right? This end, which is loose, moved up and down, and now I had the energy going in one direction, and now it's going back the other direction. So there's a reflection, but there was no inversion. The wave pulse remained upright, or unfortunately, the other term for it is it remained erect. Okay. And it's not that it stayed on the top. If the pulse was originally on the bottom orientation and remained on the bottom, that would also be remaining upright or erect. Okay. And so that change in orientation that sometimes happens during reflection is not the reflection. The reflection is this change in energy direction of transfer. Let's go to a video here. I think we can see this, right? I'm going to turn the sound off because this guy's at birds playing in the back. And there you go. You can see, boom, that the energy was traveling down this way. Now it's traveling back down this way, right? That's a fixed point. So we got the inversion, right? And notice here, his hand is also a fixed point. So I'm getting another inversion here as well. Now he's got it at a loose end, right? So it's attached to a string that's able to move, and watch what happens, right? You see that it's coming back on the same side of the equilibrium line that he sent the pulse down on, okay? So pretty clear there. There are two types of reflections. We're going to call reflections off of a fixed end a hard reflection, and a fixed off a non-fixed end soft reflection. So in a hard reflection, I get inversion. In a soft reflection, I do not. Okay, so let me, boom. So we can see like the wave going into a new medium. Here's another thing. We have a boundary. This is a very loose coiled slinky, and that is a very tight slinky. This slinky is about 10 times more massive than this. So let's see what happens here. Boom. Can you see that that slinky or that boundary act like a fixed boundary? It couldn't really move it all that much. And I know it was a fix because I get this inversion going on here. Okay. So there you go. We're going to take this down and we're going to take some notes based on this now. All right. So the first property is called a reflection. And a reflection is a wave changing the direction of energy transfer when it encounters a boundary such that the wave returns into the original medium. Okay, I'm going to put in quotes in the side about bouncing off. That's a way you want to think about it. Once again, be careful because that conceptualization does lead people to think that waves are things that are mass that can hit and interact and collide, which we don't want to do. So that's why we're going to use all those words. So I should also define for you what a boundary is. The boundary is the interface between two media. Now, with a slinky, that's pretty easy, right? Because a slinky is a linear medium. So that boundary is going to be the point where the slinky is attached to something like a wall, a string, another spring, another person holding it, whatever it is. When we start thinking about different types of multidimensional waves like water waves or sound waves, the boundaries are not going to be points, but they're going to be planes or surfaces, and things are going to get a little bit more complicated, but that's just the way to think about a boundary. Okay. So actually, before we go any further here, let's talk about what changes and what doesn't change in reflection then. Well, what changes is the direction of energy transfer. Okay. Well, what doesn't change is if I'm traveling along the slinky and reflection says I come back into the slinky and go the other direction, the medium didn't change. And if the medium doesn't change, what doesn't change? Hopefully you said to yourself, the speed of the wave doesn't change. Great. Did the source change? No, right? Same source, therefore the frequency doesn't change. And if the frequency doesn't change, neither does the period. If the speed, frequency, and period are not changing, the wavelength does not change, right? That's just one, those things follow since wavelength is the ratio of speed to frequency. Now, something that I want to talk about, what does change is the amplitude. The reflected wave is always going to have an amplitude that is smaller than the original wave. So why is that smaller than the original wave? Well, we're not seeing that in the simulation because that is a perfect situation. We saw it a little bit in the videos. It's easier to see it in some other demonstrations, but if you can imagine the wave energy is traveling down, encounters that boundary, it moves that boundary, and it's trying to transmit energy into the new medium. So actually we can see that pretty clearly here. If I look at the amplitude of the wave here compared to the amplitude of the wave afterwards, it's pretty clearly smaller because we can see some of that energy got transferred into the new medium. Okay, so it's not that the amplitude being less is because energy is lost, but it's because some of that energy is transmitted. Okay, so now let's talk about the difference between hard and soft reflections and get you some vocabulary as well as pictures. So a hard reflection, okay, this is when the boundary is fixed or I'm going to a more dense medium. Okay. And so what does that look like? If I have a wave pulse that has an amplitude of A initial going down to a wall that is fixed, right? Afterwards, there we go. The direction is opposite so that we've met our criteria for there being a reflection, but this A final, right? That A final as a magnitude is less than A initial because some of the energy has been transferred to the new medium here. Okay. So during a hard reflection, we're going to get an inversion. An inversion is just a flipping of orientation. And remember, orientation is just what side of the equilibrium line your pulse is on. All right. And then you have soft reflections. Okay. And here the boundary is loose or not fixed, right? Or off a less dense medium. And if I had my pulse, same pulse here, okay, A1 or A initial going down, and this like maybe that had that ring on it like it did in the simulation. Um, there we go. Our reflected pulse is going to be smaller again. The direction changed and back it goes. So once again, AF is less than AI. Okay. And there's no inversion. We say this remains upright or erect, right? No inversion. Now, something that I want to say here, it's going to become important in other contexts. It's hard to visualize. If we were in class, I would show this over and over and over again until people saw it. But my pictures display what I want here. Notice in both soft and hard reflections, there's a diminishment of amplitude after the reflection compared to before. But it is not accidental how I drew these. Notice here that the amplitude after the hard reflection is larger than the amplitude after the soft reflection. In a soft reflection, more of the energy is transferred into the new medium than during a hard reflection, right? So I will say more energy into the new medium, okay? Therefore, the amplitude during soft reflections decreases more than in hard reflections, right? Oh, that's so not visible. So another way to think about this, in a hard reflection, more of the energy comes back into the original medium. Therefore, the amplitude is not reduced by as much. In a soft reflection, more of it's transmitted than reflected, and therefore you get that result. Okay, so that's an important difference. There's one last thing I want to show you. Has nothing to do with reflection. I just need somewhere to tack it on. Okay. All right. So here we go. Let me get rid of this. So we said during a reflection that we're going to get a diminishment of amplitude from before to after. This simulation does not do that, right? Actually, let me just do the fixed end here. Okay. There we go. Boom. But sometimes we can see the following. And I'm going to put on something that's called damping. Essentially, what that is now as this wave is trying, or as this medium is trying to wiggle, imagine this is lying on the floor and that slinky is on the floor. And what you get is friction with the slinky and the ground. And so you get this. Notice I have a diminishment of the amplitude as it travels, right? So this is not what's happening during the reflection. This is the diminishment as it travels, and that is known as attenuation, right? Which is the gradual diminishment of the amplitude of a wave as it travels due to the work of non-conservative forces on the medium of transport, right? It's a mouthy thing, but that's what it is, right? So here you go, boom. You'll notice there I could get the reflection, but this thing is damped. It is going to attenuate as it travels, or the word attenuate literally means to make less. Okay, so I'm going to write that out. Attenuation is the gradual diminishment of amplitude of a wave as it travels due to the work of non-conservative forces on the medium of transport. Okay, two things in that I really want to call out. The gradual diminishment as it travels. So in reflection, it's not a gradual diminishment, it's a transfer to a new medium. So the amplitude was something, now it's something. That's not gradual, that's all at once. Whereas attenuation is as it's traveling, we get that diminishment. And then it's the work of non-conservative forces on the medium of transport, not on the wave, because non-conservative forces can't act on the wave. The wave's not a thing. It's acting on the thing, which is the medium of transport. Okay? So we want to get that word out there because we just saw in reflection where the amplitude decreased. And I kind of wanted to highlight that the decreasing of amplitude is not all one thing. Sometimes it's because we're trying to track where the energy is being transferred. Uh, with the case of attenuation, due to friction, through heat and sound, it's leaving the system rather than being transferred to a new medium, right? So not all amplitude changes are the same thing. So with that being said, we have the concept of reflection and this other idea of attenuation. So reflection being our first property of a wave. The next property of a wave we're going to talk about is something that is called interference.